Solving rational equations and simplifying rational expressions. When we say solving rational equations, we're basically talking about solving equations with lots of fractions in them. And you've done a lot of this before, especially this first one is a good example. What I taught you was to multiply by the common multiple, the denominators. You know that as the common denominator. So find the smallest number that 6, 5, and 6 all divide into evenly. It's the least common multiple. It's 30. So what you do is you multiply everything by 30, every term by 30. Really, on this side, you're distributing, you're taking the 30 to both. And over here, when you multiply by 30, the 6 and the 30 cancel, and you're left with 5. Now you have to distribute what's left. But notice how everything cancels. 6 and 30, the 30 becomes 5 because 6 goes into 35 times. 5 times 1 is 5. 5 goes into 36 times. 6 times x is 6x. And then I distribute the 5. 5 times x and 5 times 3. And then it just becomes a matter of solving the equation. Get the x's on one side. Hey, let's take a 5x off each side. 5 plus x equals 15. Subtract 5 from both sides. X equals 10. And I get 10 is my answer. Now what we're going to do now is go a step beyond that. Our common denominators will look like x plus 3 times x minus 2 times 5. Or maybe x times x plus 2. So we have to find that common denominator. It's the least common multiple of the denominators and multiply every term by it to cancel out all our fractions and make this equation, whatever it is, just a lot easier to solve. You have to remember when we work with fractions that had lots of x's in them, we always had to factor to get our common denominator. That's still true. You have to realize that 3x plus 3 is 3 times x plus 1. If you don't, this problem becomes a lot harder. Every denominator is going to need an x plus 1 in it. Every denominator is going to need a 3 in it and a 2 in it. The common denominator, the least common multiple, is going to be 6 times x plus 1. Now I'm going to multiply that by every term. When I do that, I can then cancel the fractions. The x plus 1s are gone. 6 times 3 is 18. 2 goes into 6 3 times. Watch out, I have to distribute this minus. Negative 3 times x plus 1 will be negative 3x minus 3. And then I'll cancel the 3 and the 6, and the 6 becomes 2. Cancel the x plus 1s, and all we're left with is 2 times 2, which is 4. This is a much easier equation. Now I can simplify. 18 minus 3 is 15. 15 minus 3x equals 4. Subtract 15 from both sides. 4 minus 15 is negative 11. And divide by negative 3. Notice that two negatives make a positive. Looks like x is 11/3. Not a very friendly answer, but one way to check it is to go to Desmos, and you could store a variable. You can't use x, you have to use like a. I'll show you what that looks like on the calculator. Plug in a and use a for x, and create the left side and the right side in Desmos, and you'll know you're correct. It will look like this. So you can't use x as a variable because x is for graphing, but I called a 11/3. That's my answer. And I used a here and here. And I did the left side of the equation, 3 over a plus 1 minus a half. I did the right side of the equation, 2 over 3a plus 3. So I have 11/3 stored in a. And now when I plug a in those two expressions, we create the same value. We can see that they are equal. So we know for 100% sure that our answer of 11/3 is correct. On this question, if I was trying to add all these expressions together, I'd have a common denominator of x plus 4 times x plus 5 times 12. Here I'm going to eliminate my fractions by using that common multiple and multiply every term by it. Every single term is going to get 12 times x plus 4 times x plus 5. Then we will cancel. The x plus 4's are gone. I'll have 12 times 1 times x plus 5. 12 times 1 is 12. 12 times x plus 5 is 12x plus 60. We have to distribute. We'll cancel the x plus 5's. Don't forget the minus. This is going to be negative 12 times x plus 4, which is negative 12x minus 48, equals, the 12's cancel. Ooh, tricky. I'm left with this. I have to FOIL it out. I have to take the x to both. That's x squared plus 5x. And I have to take the 4 to both. 4 times x and 4 times 5. This is a quadratic equation. To solve a quadratic equation, we get it equal to 0. First, let's simplify. Notice the 12x drop out. That's nice. 60 minus 18 is 12. 12 equals x squared plus 9x plus 20. Now we'll get it equal to 0 because it's a quadratic. That's how we solve a quadratic. Subtract 12. X squared plus 9x plus 8. And this factors. Factors of 8 that add to 9 are 1 and 8. So x plus 1 times x plus 8. And the solutions are what you plug in that makes 0. Because 0 times anything creates that 0. X equal negative 1 will be a solution, and x equal negative 8 will be a solution. This didn't happen here, but I want to point it out. One thing you got to watch for is look at your answers and make sure they aren't restrictions. Check the denominators. Remember here that x cannot be negative 5, and here x cannot be negative 4. If I had gotten answers of negative 5 or negative 4, I would have had to toss them, cross them out because they wouldn't work. They'd make an undefined fraction, and that can't happen. But both of these answers work fine. Again, you could check your answer. Plug this into Desmos. I'll show you how that looks. Plug it into Desmos and check it. When I plug one of those values in on the left side, I should see the fraction 1/12. Here I used a because you can't use x. So I used a. I stored negative 1 in a. And then I did 1 over a plus 4 minus 1 over a plus 5. Exactly like this question. And I had to hit the little fraction button right here. And I can see that it's 1/12. And then I tried that with negative 8. Plugging in negative 8 also works. When a is negative 8, and I plug it in that left side of the equation using a for x, I can see that when I hit the fraction button, I get that 1/12 that I'm supposed to get right there. I 100% know for certain my answers are correct. The other thing we're going to look at on this assignment is fractional exponents. And we've done some of this before. This is a quick overview. Seems like it'd been nice if the book had done this first. But either way, we learned it, and this is review for you. Reminder that when you say the square root of 2, there's a little tiny 2 here that we don't generally write. And that's a clue to us that that is 2 to the 1/2 power. And if I ask you for the cube root of 8, that is the same thing as 8 to the 1/3 power. If I ask you for the 5th root of 32, that is the same thing as 32 to the 1/5 power. In this one, what I have is 23 to the 10th power to the 1/9 power. And then you have to remember that when I say x squared cubed, that's x to the 6th. That's when you multiply your exponents. And 10 times 1/9 is 10/9. This is 23 to the 10/9 power. And we can plug that into Desmos exactly like that, 23 to the power of 10/9. and to 2 decimal spots, it ends up being 32.59. That 5 bumps the 8 to a 9. This next one is 22 to the 5th power to the 1/6, and 5 times 1/6 is 5/6. 22 to the 5/6 power. Putting that in Desmos gives about 13.14. If we keep exactly the same form, this next one would be 21 to the 5th power and the 4th root. The 4th root is 1/4. 21 to the 5th would be 5 times 1/4 is 5/4. And in Desmos, that is about 44.95. The last one, if I keep the same format as we have here, this would be 31 to the 7th power, and it would be the 8th root. So the bottom number in the fraction of the exponent, fractional exponent, is the root, and the top number is the power. 31 to the 7/8 power is 21.18. The last thing we're going to look at is how to rationalize other types of roots. Let's remember how to rationalize a square root. We've done that before. When we have a root in the denominator, we're going to rationalize it and eliminate that root. The way we do that is by multiplying by 1. You take the root part and you make it a perfect square. You multiply by root 3 over root 3 to create a perfect square. This ends up being root 9, and the square root of 9 is something I can do. Up above, I get 9 root 3. You cannot multiply those two. I can multiply a root times a root, like root 2 times root 3. That's root 6. When I take a whole number times a root, 3 times root 5, it's just like 3 times x is 3x. This is 3 root 5. Keep in mind, you really didn't do anything. It's still 3 times root 5. If we take 4 root 5 times 2 root 3, I multiply my whole numbers, that's 8, and that's 8 root 15. Root 3 times root 5 is root 15. Here then, I get 9 root 3 over the square root of 9. We don't put that 2. I'm just reminding you that you're looking for a number multiplied twice by itself makes 9, and that's 3. I cannot cancel these 3's, that's this one and this one, because one's a root and one's a whole number. That doesn't work. However, there's times here, and I can cancel. 3 goes into 9 3 times. And this simplifies then to 3 root 3. Above here, we multiplied by root 3 because it created a perfect square. Below, we need to rationalize the denominator just like we did above, but we have a cube root. We need to create a perfect cube. Notice how 25 is 5 times 5. We need one more 5 to make a perfect cube, which means what we're going to do is multiply by 1. It's going to be the cube root of 5 over the cube root of 5. What that will do is in the denominator, create a perfect cube. 7 times the cube root of 125. That's something I can do. I can get rid of that root now below. Above, I can multiply those. These are the same kind of things. Just like root 2 times root 3 is root 6. The cube root of 9 times the cube root of 5 is the cube root of 45. We can simplify this further. 2 times the cube root of 45 over 7 times the cube root of 125 is 5. That's 2 times the cube root of 45 over 35. And that is my answer. If that was a little confusing, I will do more examples of this in the homework part of the video. at least 2. So watch those. This takes practice and is a little strange. You can rationalize the denominator with any kind of root. If this had been a 5th power, then I would have multiplied and tried to make a perfect 5th root. If it had been a 4th power, I would have multiplied by 1, just like I did here, and tried to make a perfect 4th root. So it just takes a little practice, but it's the same process you do with the square root. It's just that you have a different kind of root. The rest of this video is questions from your assignment. Question 2. We're going to get rid of fractions to make this much easier to solve. To do that, we need the common multiple of the denominators. It's the common denominator. If we were adding and subtracting them, it would be what we would use to add and subtract them. If your denominator has an x in it, every denominator is going to need that x. If my denominator has a 3 in it, every denominator is going to need that 3. It's like we're adding them, but we're not. We're going to cancel our fractions. We'll multiply everything by 3x. That will cancel every fraction. Do not forget the minus 4. Every term gets it. Here the x's cancel. I am left with 3 times negative 10. That's negative 30. Here the 3x's cancel. So this will be equal to negative 8. And 4 times 3x, so this is minus 12x. We'll add 8 to both sides. And that is negative 22 equals negative 12x, and divide by negative 12. Notice that 2 negatives make a positive when you divide, and these both divide by 2, and I get 11 over 6. 11 over 6 is my answer. Question 4. There are 2 ways you could do this. Because there's a single fraction on each side, if you wanted, you could cross multiply. That only works because there's a single term on each side. If there'd been a plus 2 out here, you couldn't cross multiply unless you got a common denominator and combine like that right half. It's easier usually just to multiply by the common multiple, that's the common denominator, and eliminate all your fractions. The common multiple would be x plus 3 times x minus 3. Multiply both sides by that. We can cancel the x minus 3's on this side and the x plus 3's on this side. Distribute negative 3 through the parentheses. Negative 3x plus 9. Distribute 2 through the parentheses. It's equal to 2x plus 6. Add 3x to both sides. 9 equals 5x plus 6. Take a 6 off each side. That's 3 equals 5x. Divide by 5. And it looks like x is 3/5. There's only one non-extraneous root. An extraneous answer is one that doesn't work because it's a restriction. So it's very possible here that when we solve this thing, one of them is a restriction. Remember that we know x cannot be 1. We know that x cannot be negative 3. And here we need to factor this. X times x is x squared, positive and negative to make negative 3. And the factors of negative 3 that add to positive 2, that would be positive 3 and negative 1. So it looks like those are the same 2 restrictions. X can't be 1 and x can't be negative 3. Let's write this below. We need to multiply by the common denominator, which is going to be x minus 1 times x plus 3. Multiplying every term by that will cancel out every denominator, which is what we want to have happen. Here we'll cancel the x minus 1's and we get x plus 3 times x plus 1. Here we'll cancel out the x plus 3's and we have negative 2 times x minus 1. We'll cancel out the x minus 1's and the x plus 3's, and we're left with 8. We need to FOIL this. The inside will make 3x, and the outside will make 1x. So this will be x squared plus 4x plus 3, 1 times 3. Distribute that negative 2, negative 2x plus 2 plus 8. Let's simplify. This is x squared plus 4x plus 3 equals negative 2x plus 10. Now we're going to move that negative 2x over and this 10 over, get it equal to 0. That's how we solve a quadratic. This becomes x squared, and we add 2x to both sides, so plus 6x. And we subtract 10 from both sides, that's minus 7 equals 0. This factors because there are factors of 7 that subtract to 6, or factors of negative 7 that add to positive 6. It's a plus and minus to make negative 7, and it's positive 7 times negative 1. My solutions are what makes 0. Here, plugging in negative 7 would create 0, and here, plugging in 1 would create 0, because again, 0 times anything will be equal to 0. The problem is, if you look at the original question, x could not possibly be 1, because if x was 1, you'd be dividing by 0 here and here. X cannot be 1. It's called an extraneous solution. It doesn't work in the original equation. This is our answer then, x equals negative 7. This expression with fractional exponents. So we did this with logarithms. It was the idea that the square root, remember there's a little 2 here we don't put, of 100 is 100 to the 1/2 power. And the cube root of 27 is 27 to the 1/3 power. So if I ask you to do the 5th root of 32, say cubed, well that's 32 to the 1/5 cubed, and this is the situation where we multiply our exponents, which is 32 to the 3/5. Just observe that the bottom part of the fractional exponent is the root. In other words, right here is the 5th root. And the top part is the power. In this question, the 5th root of x cubed would be x cubed to the 1/5 power, which would be x, when you multiply those, 3 times 1/5 is 3/5, x to the 3/5. In question 16, this is 1 over x cubed to the 1/4 power, which is 1 over x to the 3/4. Now, that would be the correct answer, but they may want it with just a fractional exponent, no fraction. This would be x to the negative 3/4. Remember how x to the negative second was 1 over x to the second? Well, I could say that 1 over x to the 5th is x to the negative 5th, and that's the idea here. By writing it as a negative power, I can eliminate this fractional part. Both of these technically are correct. I'm going to see if it accepts the first one. I did just check, and they didn't want that answer, they want this one. As I said, those two are equal, but we're looking for just a variable to a power in this question. Question 21 is a calculator question. I will point out that you could write this as 1,296 to the 1/4 power. You can put it in either this way or this way in Desmos, and it will give you the same answer. I'll show you. In Desmos, I brought up the keyboard, click in the lower left corner, and under miscellaneous, you can do any root and plug in the question like this. But that's the same thing as 1,296 to the 1/4 power. Both of these give you the same answer of 6. 6 here is the answer to the first one. This one then is the opposite of that, -6. Now this is just like taking the square root of -16. We know how to make that -1 times 16, which is 4i. You might vaguely remember that. But this is an imaginary number. And what they say here is if it's not a real number, enter DNE. You can't take any even root of a negative for the same reason you can't take the square root of a negative. There's no number multiplied an even number of times that makes a negative. Not possible. This then is DNE. The answer does not exist. 8 to the 4/3 power is 8 to the 1/3 to the 4th power, which is the cube root of 8 to the 4th power. The cube root of 8 is 2 because 2 times 2 times 2 3 times makes 8. This is 2 to the 4th power then. And 2 to the 4th power, 2 times 2 times 2, 4 times, happens to be 16. In question 30, we are going to rationalize the denominator, meaning we're not going to allow any square roots in that denominator. Now, 81 happens to be 9 times 9, and we have a cube root. We only need one more 9 to make a perfect cube. What we'll do then is take this 8 times the cube root of 5 over 7 times the cube root of 81, and we'll multiply by something that makes that a perfect cube so that we can eliminate that root. We need one more 9. We've got 2 of them here. We need one more. So we'll multiply by the cube root of 9. This will be 8 times the cube root of 45 over 7 times the cube root of 729. Now we know that this is 9 times 9 times 9. It's 9 cubed. And the cube root of 9 cubed would be 9. This is 8 times the cube root of 45 over 7 times 9, which gives us a final answer of 8 times the cube root of 45 over 63. And if 8 and 63 had any common factors, I would simplify that, but they don't. Question 31, a little like the previous one. We're going to rationalize the denominator, and we have a 25 below, which happens to be 5 times 5. To make a perfect cube, I only need one more 5. I'm going to multiply the top and the bottom by the cube root of 5. This becomes 9, and since these are both cubed root, I can multiply them. 9 times the cube root of 15 over 8 times the cube root of 125. That is 9 times the cube root of 15 over 8 times 5. The cube root of 125 is 5, which is 9 times the cube root of 15 over 40. Again, you would always look to see if maybe the whole number parts canceled. You have multiplication here. If they had any common factors, you could cancel. But since there are no common factors, that is my answer.